Before we begin, please take a moment to hit that like button and subscribe to this channel. Your support really helps, and I promise that what you are about to hear will leave you looking at the night sky very differently. Tonight, we are going to talk about something that keeps astronomers up at night. Not because they are scared, but because they are confused. Genuinely confused. Out there in space, we have discovered things that do not make sense. Things that should not exist according to everything we know. Things that break the rules. I am not talking about science fiction or speculation. I am talking about real observations, things we have actually seen and measured, things that are out there right now doing whatever strange thing they do, and we have no idea why. Over the past few decades, as our telescopes have improved, we have stumbled across discoveries that have left scientists scratching their heads. Some challenge our understanding of physics. Some suggest there might be processes we do not know about yet, and some are just plain weird. Let me start with something that happened on August 15, 1977. A man named Jerry Emmon was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was part of the search for extraterrestrial intelligence, SETI. Every day it scanned the sky, listening for radio signals that might indicate intelligent life somewhere out there. Most days, the data was boring. Background noise from space, nothing unusual. But on this particular day, Emmon saw something that made him grab a red pen and write "wow" in the margin of the printout. That is why we call it the "wow" signal. The signal lasted 72 seconds. During that time, it was 30 times stronger than the background noise. It came from a specific direction in the constellation Sagittarius. And here is what makes it so interesting. The signal's frequency was around 1420 megahertz, right near the hydrogen line. Hydrogen is the most common element in the universe. If you were an alien civilization trying to send a signal that others might recognize, you might choose a frequency related to hydrogen. It is like picking a universal language based on something everyone would know. The Big Ear telescope had two receivers that scanned the same patch of sky 3 minutes apart. The signal showed up on the first receiver but not the second. That means it lasted less than 3 minutes, probably closer to 72 seconds. Since 1977, astronomers have gone back to that same spot in the sky dozens of times, using more powerful telescopes, listening at the same frequency and nearby frequencies. Nothing. The "wow" signal was a one-time event. Now, I need to be clear about the uncertainty. The signal could have been artificial or natural. The Big Ear telescope could not pinpoint locations precisely, so we know the general direction but not the specific source. Some scientists have proposed natural explanations. Maybe it was a signal from a passing comet. Comets can emit radio waves when the solar wind interacts with their hydrogen clouds. In 2016, a researcher named Antonio Paris suggested that two comets, 266P/Christensen and P/2008Y2, were in that region of space at the time. But there is a problem with the comet theory. The signal was incredibly narrowband. It occupied a very specific frequency. Natural sources usually produce signals across a broader range of frequencies. The narrowness of the "wow" signal is more consistent with an artificial source, something deliberately transmitting on a chosen frequency. Other scientists have suggested it might have been interference from Earth, a satellite, an aircraft, or some ground-based transmitter that happened to send a signal at just the right time. But the Big Ear telescope was designed to filter out terrestrial interference, and the signal came from a direction that was not consistent with any known satellite or aircraft at the time. So what was it? Honestly, it remains unexplained. Nearly 50 years later, the "wow" signal is still one of the most intriguing unexplained observations in the history of SETI. The fact that it never repeated is both frustrating and significant. If it was an alien civilization, why would they transmit only once? Maybe they were using a lighthouse strategy, sweeping a beam across the galaxy, and we just happened to catch it for a brief moment. Maybe it was a one-time broadcast. Maybe it was not meant for us at all. Just accidental spillover from some other communication. Or maybe it was not aliens. Maybe it was some natural phenomenon we do not understand yet. The universe is full of processes that emit radio waves, pulsars, quasars, magnetars, supernova remnants. We are constantly discovering new types of radio sources. Maybe the "wow" signal was something natural that we have just never seen before or since. The answer may never come. It is a mystery frozen in time. But it is also a reminder of how much remains unexplained. Somewhere out there in the direction of Sagittarius, something sent out a powerful narrowband radio signal, and we happened to catch it. That is either the most incredible coincidence in the history of astronomy, or it is evidence of something extraordinary. Now let us talk about something that is happening right now. A star that has been driving astronomers crazy since 2011. Its official name is KIC 8462852, but most people call it Tabby's star, named after astronomer Tabitha Boyajian, who led the research team studying it. Tabby's star sits about 1,460 light-years away in the constellation Cygnus. It looks like an ordinary star, slightly larger and hotter than our Sun. Nothing about it should make it special. But in 2011, the Kepler Space Telescope noticed something weird. Stars dim sometimes. That is normal. If a planet passes in front of a star from our perspective, the star's light drops slightly. That is how we detect exoplanets. When Earth passes in front of the Sun from another star's perspective, the Sun's light would dim by about 0.01%, tiny but measurable. Jupiter would cause a dimming of about 1%. That is the kind of dimming we expect from planets. Regular, predictable, small. Tabby's star does not do that. In 2011, its light dropped by 15%. Then it came back. In 2013, it dropped by 22%. Then it came back again. The dimmings were irregular. They did not repeat at predictable intervals. They lasted different amounts of time. Sometimes the star would dim a little, sometimes a lot. 22% is enormous. A planet the size of Jupiter would only block 1% of the star's light. To block 22%, you would need something absolutely massive, something as large as the star itself. The initial discovery set off a frenzy of theories. One suggestion was an alien megastructure. The idea comes from a hypothetical concept called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson wondered what an advanced civilization would do if it needed enormous amounts of energy. Eventually, he reasoned they might build structures around their star to capture its energy output. Not a solid shell, which would be impossible, but a swarm of energy-collecting satellites. If you were building something like that, it would block varying amounts of the star's light as the structure orbited. It would be irregular. It would dim the star by large amounts. It would look exactly like what we were seeing with Tabby's star. Before you get too excited, let me be clear. Most astronomers do not think Tabby's star is an alien megastructure. The alien hypothesis was always the least likely explanation. But here is the thing. We had to consider it because we could not explain the observations any other way. That is how weird this star is. So, if it is not aliens, what is it? Scientists proposed several natural explanations. Maybe there is a giant swarm of comets orbiting the star. If a family of comets passed in front, they would block light irregularly. Their dust tails would create uneven dimming. This was a leading theory for a while, but there are problems. You would need an enormous number of comets to block 22% of the star's light. And comets would produce dust, which would make the star appear redder when it is dimmed. Tabby's star does not do that. The color stays the same even when it is dimmed. Another theory suggested a recent collision. If two large objects smashed together near the star, the debris cloud could block light irregularly as it spread out. But again, we would expect to see excess infrared radiation from warm dust. We do not see that. Some scientists suggested the dimming might be caused by the star itself. Maybe it is a variable star that dims naturally. But Tabby's star does not show the characteristics of known variable stars, and the dimming pattern is too irregular. Then, in 2017, astronomers made another observation. They caught Tabby's star dimming again and observed it across multiple wavelengths of light. What they found was interesting. The dimming was more pronounced in blue light than in red light. That is consistent with dust blocking the starlight. Small dust particles scatter blue light more effectively than red light, the same reason Earth's sky is blue. So maybe it is dust after all. But if it is dust, where is it coming from? Why is there so much of it? Why is the pattern so irregular? The latest observations suggest that Tabby's star might have a large debris field around it, perhaps from a destroyed planet or a massive collision. The debris blocks light irregularly as it orbits. This is the current leading explanation, but it is not fully satisfying. And here is what makes this even stranger. Tabby's star is still doing it. We have now watched this star for more than a decade. Keeps dimming in weird, unpredictable ways. We have multiple data sets from different telescopes. The phenomenon is real, it is not a measurement error or a glitch. Something is actually blocking the light from this star in ways that remain puzzling. As of today, Tabby's star remains one of the strangest objects in the sky. Out of hundreds of billions of stars, this is the only one that behaves like this. Maybe one day we will figure it out. Maybe it is a natural process we just have not encountered before. Or maybe it is something else entirely, something we have not even thought of yet. Let me tell you about something that scientists discovered in 2019 that absolutely should not exist. They are called odd radio circles, ORCs. The name is perfect because they are odd. They are circles, and we only see them in radio wavelengths. Here is what they look like. If you point a radio telescope at certain parts of the sky, you see a perfect circle. The circle is enormous, hundreds of thousands of light years across. And here is the weird part. There is usually a galaxy at the center. The first one was discovered by a team led by astronomer Ray Norris. They were using the Australian Square Kilometre Array Pathfinder Telescope, SCAP, to survey the radio sky. When the team processed their data, they found these circular structures. At first, they thought it was a processing error. Circles are suspicious in astronomy. Nature rarely makes perfect circles. But when they checked the data carefully, the circles were real. They found 3 more. Then other telescopes confirmed them. As of today, we have found about a dozen ORCs. They are rare, they are large, and their origin remains a puzzle. Let me describe what we are seeing. Each ORC is a ring or shell of radio emission. The ring is nearly circular, sometimes perfectly so. At the center, there is usually an elliptical galaxy. That galaxy appears normal at optical wavelengths. There is nothing obvious about it that would explain the radio ring around it. The rings are enormous. Some are more than 1 million light-years across. That is 10 times the diameter of the Milky Way. These are huge structures. Now, astronomers see circular things in the sky. Sometimes supernova remnants can look circular. They are expanding shells of debris from exploded stars. But supernova remnants are much smaller and are associated with recent stellar explosions. ORCs are too large and too far away to be supernova remnants. Planetary nebulae can also look circular shells of gas shed by dying stars. But again, they are much smaller and are inside our own galaxy. ORCs are definitely not planetary nebulae. Some galaxies have radiolobes where jets from a central black hole shoot matter out into space, which can create circular structures when viewed from certain angles. But ORCs do not match the characteristics of radio galaxies. The central galaxies do not show the active supermassive black holes that would be needed to create such structures. So what are they? Honestly, we do not know. Scientists have proposed several theories. Maybe they are shock waves from massive explosions in the center of galaxies. If a galaxy went through a period of intense star formation, or if its central black hole suddenly became active, it could create a blast wave that expands outward. Over millions of years, this wave could create a spherical shell of radio emission. But if that is the case, why do we not see more of them? Galaxies go through active phases all the time. We should see these structures more often. Another theory suggests they might be related to merging galaxies. When 2 galaxies collide, all sorts of crazy things happen. Maybe the collision creates shock waves that expand outward as spherical shells. But again, galaxy mergers are common, yet ORCs are rare. Some scientists have suggested even more exotic explanations. Maybe they are the imprints of primordial events from the early universe, or related to cosmic strings, or some other esoteric feature of spacetime. These ideas are highly speculative. The truth is we are still in the discovery phase with ORCs. We have only known about them for a few years. We need more observations. We need to find more of them. We need to study the galaxies at their centers in more detail. What makes ORCs particularly fascinating is that they represent something genuinely new. We have been studying the radio sky for decades, but ORCs only showed up when we built more sensitive radio telescopes. They were always there, we just could not see them until recently. Every time we build a better telescope or observe in a new wavelength, we find something unexpected. ORCs are a perfect example. Nobody predicted them. Nobody was looking for giant radio circles around galaxies. They were a complete surprise. Now let us talk about something that breaks the rules on a truly cosmic scale. In 2021 and 2024, astronomers discovered two enormous structures that challenge one of the fundamental principles of cosmology. The first is called the Giant Arc. It was discovered by Alexia Lopez, a PhD student at the University of Central Lancashire. The Giant Arc is a structure of galaxies that spans about 3.3 billion light-years. That is not the distance to it, that is how large it is. The structure itself is 3.3 billion light-years across. To put that in perspective, light takes 3.3 billion years to travel from one end of the structure to the other. The entire observable universe is only 93 billion light-years across. This structure is a significant fraction of that. The Giant Arc is located about 9.2 billion light-years from Earth. It appears as a curved arrangement of galaxy clusters, like a giant arc in the sky, hence the name. Then, in 2024, the same research team found something else. They call it the Big Ring. This is another enormous structure about 1.3 billion light-years in diameter. It is also located about 9.2 billion light-years away, and here is the kicker. It is in the same region of the sky as the Giant Arc. Two enormous structures, both in the same part of the universe, both at the same distance. That suggests they might be related somehow. Why is this a problem? In cosmology, there is something called the cosmological principle. This principle states that when you look at the universe on large enough scales, it should be roughly uniform. No matter which direction you look, you should see roughly the same density of matter. The universe should be homogeneous and isotropic at large scales. This principle is fundamental to our understanding of the universe. It is built into the standard model of cosmology and is supported by observations of the cosmic microwave background, which shows that the early universe was remarkably uniform. But the Giant Arc and the Big Ring challenge this principle. They are too large. According to calculations based on the standard model, structures should not be able to grow larger than about 1.2 billion light-years. That is the theoretical limit based on how gravity has had time to pull matter together since the Big Bang. The Giant Arc is nearly 3 times larger than this limit. Even the Big Ring at 1.3 billion light-years is pushing the boundary. If these structures are real, and they appear to be, then either our theoretical limit is wrong or something weird is going on. Maybe the cosmological principle does not hold as well as we thought. Maybe the universe is lumpier than we believed. Maybe there are processes we do not understand that can create structures larger than theory predicts. Some astronomers have questioned whether these structures are real or just statistical flukes. When you look at the distribution of galaxies, you can sometimes see patterns that are not really there. Your brain looks for connections. But Alexia Lopez and her team did careful statistical analysis. The probability of the Giant Arc being a random arrangement is about 1 in 6,000, pretty low. The structure appears to be real. The Big Ring statistics are even more compelling. And the fact that both structures are in the same region of space makes a coincidence even less likely. So what are they? One possibility is that they are related to baryon acoustic oscillations, sound waves that traveled through the hot plasma of the early universe, leaving an imprint on how matter is distributed. But the Giant Arc and the Big Ring do not match the expected size from those oscillations. They are much larger. Another possibility is that they are related to cosmic strings, hypothetical one-dimensional defects in spacetime predicted by some theories but never observed. If cosmic strings exist, they could create large-scale structures as galaxies form preferentially along them. But cosmic strings are speculative. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle is not as robust as we thought. Maybe the universe has large-scale structure that we did not account for. This would not mean the Big Bang theory is wrong. It would mean we need to refine our understanding of how structure formed. That is how science works. You make observations, build models, and when observations do not match models, you update the models. Let me tell you about a place in the universe that is almost empty. It is called the Boötes Void, and it is one of the strangest features of the cosmic landscape. The Boötes Void is a region of space about 330 million light-years across. That is more than 3,000 times the diameter of the Milky Way, an enormous volume. Here is what makes it strange. This volume should contain about 2,000 galaxies based on the average density of the universe. But when astronomers survey the Boötes Void, they find only about 60 galaxies. The rest is empty. It is not completely empty. There are a few dozen galaxies scattered throughout, but compared to what should be there, it is remarkably void of matter. The The Boötes void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping the distribution of galaxies and noticed this huge empty region in the constellation Boötes. Initially, they were not sure if it was real or just an artifact of their survey. Maybe they had missed some galaxies. But follow-up observations confirmed it. The void is real. There really is a huge bubble of space with almost no galaxies in it. Now, voids are not unusual. The cosmic web consists of filaments of galaxies surrounding voids. Most voids are tens of millions of light-years across. But the Boötes void is special. It is much larger than typical voids. It is one of the largest known supervoids in the nearby universe. And its existence raises questions about how structure formed in the cosmos. The universe started out almost perfectly uniform. The cosmic microwave background shows that at 380,000 years after the Big Bang, matter was spread almost evenly through space. There were tiny density variations, but they were incredibly small. Over time, gravity amplified these variations. Regions that were slightly denser attracted more matter and became even denser. Regions that were slightly less dense lost matter to their surroundings and became voids. Computer simulations of this process can reproduce the cosmic web we see today. Filaments, clusters, and voids all emerge naturally from gravity acting on the initial density variations. But the simulations also predict limits. Voids can only grow so large given the age of the universe and the strength of gravity. The Boötes void is close to this limit. It is about as large as voids can theoretically get. That makes it an extreme example, testing our understanding of structure formation. If we ever find voids much larger than the Boötes void, it would suggest something is wrong with our models. There is another interesting aspect to the Boötes void. The few galaxies inside it are weird. Some are forming stars at unusually high rates. Some have unusual shapes or characteristics. It is as if the isolation has affected them somehow. Think about it. If you are a galaxy in a dense region, you are constantly interacting with other galaxies, pulling on them gravitationally, sometimes colliding and merging, exchanging gas. You are part of a busy neighborhood. But if you are a galaxy in the Boötes void, you are alone. Your nearest neighbor might be millions of light-years away. You evolve in isolation, without the gravitational harassment that galaxies in dense regions experience. This isolation might change how you evolve. Maybe you retain more gas, maybe your star formation happens differently. The galaxies in the Boötes void give us a chance to study what happens to galaxies when they are isolated. But the fundamental question remains: why is the Boötes void so empty? The answer probably goes back to the initial conditions of the universe. This region must have started out with a slightly lower density than average. Over billions of years, gravity pulled matter out of the region toward denser areas, creating the void we see today. But why was this region less dense to begin with? That relates to whatever process created the initial density variations in the very early universe. Most cosmologists think these variations came from quantum fluctuations during the inflationary epoch, a brief period of exponential expansion right after the Big Bang. These quantum fluctuations were random. Some regions ended up slightly denser, some slightly less dense. Most variations were small, but occasionally, by chance, you would get a larger variation. The Boötes void might be the result of one of these chance larger variations in the initial conditions. It is remarkable when you think about it. The emptiness we see today, 330 million light-years across, originated as a tiny quantum fluctuation in the first fraction of a second after the Big Bang. Speaking of the early universe, let me tell you about one of the most peculiar features in the cosmic microwave background. It is called the CMB cold spot, and it has been puzzling cosmologists since 2003. The cosmic microwave background, the CMB, is the afterglow of the Big Bang. When the universe was 380,000 years old, it cooled enough that electrons and protons could combine to form neutral hydrogen. Before this, the universe was opaque. Photons could not travel far. After this, the universe became transparent, and photons could travel freely. The CMB is made of those photons. They have been traveling through space for 13.8 billion years, and we see them today as a faint microwave glow coming from all directions. The remarkable thing about the CMB is how uniform it is. If you measure its temperature in different directions, it is almost exactly the same everywhere, about 2.725 Kelvin, just a few degrees above absolute zero. But there are tiny variations. Some regions are slightly warmer, some slightly cooler. The temperature differences are about 1 part in 100,000. These variations are the imprints of density fluctuations in the early universe. Regions that were slightly denser were slightly cooler in the CMB, and those dense regions eventually became the galaxies and galaxy clusters we see today. Satellites like COBE, WMAP, and Planck have mapped the CMB in exquisite detail. And when scientists analyzed these maps, they found something unexpected. There is a region of the sky about 10 degrees across that is significantly cooler than expected. This is the CMB cold spot. It is not just a little bit cooler, it is about 70 millionths of a degree cooler than the average. That might sound tiny, but in the context of the CMB's tiny variations, it is huge. The cold spot is located in the constellation Eridanus. It is oval-shaped, spanning about 10 by 5 degrees, roughly 50 times the apparent size of the full moon. Here is why it is strange. Based on our standard model of cosmology, we can calculate the probability of such a large cold region appearing by chance. The probability is about 2%. Not impossible, but unlikely. 2% means that if you ran the universe 100 times with random initial conditions, you would expect to see a cold spot like this in about 2 of those universes. We live in one universe. So either we are just unlucky and happen to be in one of the 2%, or there is something special about the cold spot. Scientists have proposed several explanations. One idea is that the cold spot is caused by a supervoid. Remember, voids are regions of space with few galaxies. If there is an enormous void between us and the CMB in this direction, photons passing through it would lose energy due to something called the integrated Sachs-Wolf effect. Here is how it works. As photons enter a void, they climb out of a gravitational well, losing energy. As they leave the void, they fall into a gravitational well, gaining energy. If the universe were not expanding, these effects would cancel out. But because the universe is expanding, the void gets larger and less dense while the photons are crossing it. This means they gain less energy on the way out than they lost on the way in. The net result is that the photons end up cooler. So a supervoid could create a cold spot in the CMB. Indeed, astronomers have found evidence of a large void in the direction of the cold spot. It is not as large as the Boötes void, but it is still substantial. However, even with this void, calculations suggest it can only account for a small part of the cold spot's coldness. You would need an absolutely enormous void to explain the full effect, and we do not see evidence of a void that large. Another theory suggests the cold spot might be related to a collision between our universe and another universe in a multiverse scenario. In some versions of cosmic inflation theory, our universe is just one bubble in an infinite foam of universes. If another universe bubble collided with ours early on, it would leave a mark in the CMB, a circular region that is colder or warmer than average. This is an exotic explanation, and there is no direct evidence for it beyond the cold spot itself. But it shows how puzzled scientists are. They are willing to consider multiverse collisions because conventional explanations do not quite work. A third possibility is that the cold spot is just a statistical fluke. 2% probability means it is rare but not impossible. Maybe we just happen to live in a universe where this unlikely feature exists. The challenge is that we only have one CMB to observe. We cannot run the experiment again. We have one data point, the universe we live in. This makes it hard to know if the cold spot is a meaningful anomaly or just chance. As of today, the CMB cold spot remains unexplained. It might be caused by a supervoid, but probably not entirely. It might be a statistical fluke, but that seems unsatisfying. It might be evidence of exotic physics, but that is highly speculative. What is clear is that it stands out in the CMB maps. It is larger and colder than our models predict. Now let us talk about a star that breaks the rules of nuclear physics, or at least seems to. It is called Przybylski's star, officially designated HD 101065. It is located about 370 light-years away in the constellation Centaurus. From a distance, Przybylski's star looks normal. It is an A-type star, about twice as massive as the Sun and about 6 times more luminous. Nothing unusual there, but when astronomers analyzed its light spectrum, they found something absolutely bizarre. The star contains elements that should not exist in any star for more than a few weeks. Specifically, it contains technetium, promethium, and other radioactive elements with short half-lives. Let me explain why this is a problem. Stars create elements through nuclear fusion. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. In the most massive stars, the process continues, creating heavier and heavier elements up to iron. Elements heavier than iron are created in supernova explosions and other energetic events. When a massive star explodes, the incredible pressures and temperatures create these heavy elements, which are scattered into space and can be incorporated into new stars. So when we see heavy elements in a star's atmosphere, we assume they were there when the star formed. The star was born from a cloud of gas that contained material from previous generations of stars. But here is the catch. Some heavy elements are radioactive. They decay over time. Uranium, for example, has a half-life of about 4.5 billion years. Technetium, on the other hand, has no stable isotopes. All forms of technetium are radioactive. The longest-lived isotope, technetium-98, has a half-life of about 4.2 million years. That is nothing on cosmic timescales. Przybylski's star is probably several billion years old. It is a mature star, not a young one. If it formed with technetium in its atmosphere, that technetium would have decayed away billions of years ago. There should be none left. Yet, when astronomers observe the star's spectrum, they see clear evidence of technetium. They also see promethium, another radioactive element with a short half-life. And they have seen these elements consistently since the star was first studied in detail in the 1960s. So where is this technetium coming from? There are a few possibilities, none of them completely satisfying. One idea is that the star is creating technetium on its surface through some unknown nuclear process. Maybe there is a mechanism we do not understand that can produce these elements in the star's atmosphere. But this seems unlikely. We have a pretty good understanding of nuclear physics, and there is no known process that could do this in the cool outer layers of a star. Another idea is that the technetium is being brought up from the star's interior. Maybe deep inside the star, nuclear reactions are creating technetium, and convection currents are carrying it to the surface. But again, this does not quite work. The star's interior is not hot enough to create technetium through normal nuclear reactions. A third idea, which sounds like science fiction, is that the star contains superheavy elements, elements with atomic numbers far beyond anything we have seen. In theoretical nuclear physics, there is something called the island of stability. The idea is that if you go far enough up the periodic table, you might find a region where certain superheavy elements are relatively stable. Some of these superheavy elements, if they exist, might decay into technetium and promethium as intermediate products. So the star might contain superheavy elements that are slowly decaying, replenishing the supply of technetium and promethium. This is highly speculative. We have never observed superheavy elements in nature. We have created a few in particle accelerators, but they decay almost instantly. The island of stability is a theoretical prediction, not an established fact. Still, Przybylski's star is so weird that astronomers are willing to consider exotic explanations. Another strange thing about the star is its composition. It has unusually high amounts of certain rare earth elements. Its spectrum shows strong lines of elements like holmium, dysprosium, and europium, much more abundant than in the Sun. It is what is called a chemically peculiar star. There are several types of chemically peculiar stars, and they are thought to arise because of atmospheric processes that concentrate certain elements. Radiation pressure and magnetic fields can cause some elements to sink or float in the star's atmosphere, creating unusual abundances. But even among chemically peculiar stars, Przybylski's star is exceptional. Its abundance patterns are more extreme than almost any other star, and the presence of short-lived radioactive elements is unique. Some astronomers have wondered if Przybylski's star might have a companion. Maybe it is in a binary system with a neutron star or white dwarf, and material from the companion is falling onto the star, bringing radioactive elements with it. But we see no evidence of a companion. The star's motion does not show the wobble we would expect from an orbiting partner. As of today, Przybylski's star remains a mystery. For more than 60 years, astronomers have been observing it, and for more than 60 years it has shown technetium and promethium in its spectrum. These elements should have decayed away long ago, yet they are still there. Either there is a nuclear process we do not understand, or the star contains exotic matter, or there is something fundamentally wrong with our observations or interpretations. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii detected something moving through the solar system. At first, they thought it was a comet or asteroid, but as they gathered more data, they realized this object was different, very different. They named it Oumuamua, a Hawaiian word meaning scout or messenger, and it was the first confirmed interstellar object to pass through our solar system. Oumuamua came from outside the solar system, from interstellar space. It approached from the direction of the constellation Lyra, passed through the inner solar system, and was headed back out into interstellar space. We only had a few weeks to study it before it became too faint and distant to observe. What we learned during those weeks was fascinating and confusing. First, its shape. Based on how its brightness varied as it tumbled through space, astronomers calculated that Oumuamua was extremely elongated. The best estimates suggested it was about 400 meters long and only about 40 meters wide, a ratio of 10:1. It was cigar-shaped, or maybe more like a pancake depending on the exact geometry. This is unusual. Most asteroids and comets are more spherical or irregular, not long and thin. Second, its surface. Oumuamua was reddish in color, similar to some objects in the outer solar system, which suggested its surface had been exposed to cosmic rays for a long time. So far, that is normal. But Oumuamua showed no signs of a coma. Comets, when they get close to the sun, heat up. Ice on their surface vaporizes, creating a cloud of gas and dust called a coma. Oumuamua did not have a coma, even when it passed close to the sun, well inside Mercury's orbit. This suggested it was not a comet, at least not a typical icy comet. Maybe it was more like an asteroid made of rock or metal. But then came the really weird part. Oumuamua's trajectory did not match what we expected. After it passed the sun and was heading back out of the solar system, it was accelerating slightly more than it should have. Based on gravity alone, the gravitational pull of the sun and planets, we could predict exactly where Oumuamua should be at any given time. But it was moving slightly faster than expected. It was being pushed by something other than gravity. This is normal for comets. The evaporating gas from a comet's coma creates a rocket effect, pushing the comet slightly. But Oumuamua did not have a coma. So what was pushing it? Scientists proposed several ideas. Maybe Oumuamua was outgassing, but the gas was not carrying enough dust to create a visible coma. Maybe it was venting gas from one side, creating thrust, but we just could not see it. Some observations suggested there might be very faint traces of gas, but it is hard to be sure. Another idea was that Oumuamua was being pushed by sunlight. All objects in the solar system experience radiation pressure. Photons from the sun hit the object and transfer momentum, pushing it slightly. For most objects, this force is tiny, much smaller than gravity. But if an object is very thin and light, like a sheet or sail, radiation pressure can be significant. Maybe Oumuamua was very thin, more like a pancake than a cigar. If it was only a few meters thick but hundreds of meters across, and if it was made of relatively light material, radiation pressure could explain the observed acceleration. But this raises questions. How would such an object form naturally? Why would it be so thin? It is hard to imagine natural processes creating a thin, rigid sheet of rock or ice hundreds of meters across. This is where things get really speculative. In 2018, two Harvard astronomers, Abraham Loeb and Shmuel Bialy, published a paper suggesting that Oumuamua might be artificial. Specifically, they suggested it could be a light sail, a thin, reflective sheet designed to be pushed by starlight. Such a sail could be a spacecraft or a probe sent by an alien civilization. This suggestion generated a lot of controversy. Most scientists were skeptical. The alien hypothesis is always the last resort in astronomy. You only invoke aliens when you have exhausted all natural explanations. And there were natural explanations for Oumuamua, even if they were a bit strained. Loeb argued that we should at least consider the possibility. If Oumuamua was artificial, it would be the most important discovery in human history. The fact that it is unlikely does not mean we should dismiss it without consideration. But most astronomers think Oumuamua is natural, probably a comet with unusual properties, or an asteroid with a weird shape, or perhaps a piece of a shattered planet from another star system. These explanations require fewer assumptions than aliens. The problem is we will never know for sure. Oumuamua is gone. It is too far away and too faint to observe now. We had a few weeks to study it, and we did not get all the data we wanted. If another interstellar object passes through the solar system, we will be better prepared. We will have more telescopes ready. We will get more detailed data. In fact, a second interstellar object was discovered in 2019. It is called 2I/Borisov, and it is definitely a comet. It has a coma and a tail and behaves exactly like comets in our solar system do. Borisov is unremarkable, which makes it remarkable. It shows that interstellar comets are pretty much like solar system comets. But Oumuamua remains unique. We have never seen another object quite like it. Maybe it was just a weird natural object. Maybe it was something more. We will probably never know. In June of 2018, telescopes around the world detected a bright explosion in a galaxy 200 million light-years away. They labeled it at 2018 COW. The name comes from the automated naming system for astronomical transients. The COW part is just random letters, but it has become the nickname for this event. At first, astronomers thought it was a supernova. Supernovae are exploding stars, and they happen regularly. We detect dozens every year. But as they gathered more data, they realized that 2018 COW was different. Very different. First, it was extremely bright, about 10 to 100 times brighter than a typical supernova. And it got bright fast. Most supernovae take weeks to reach peak brightness. A 2018 COW reached peak brightness in just a few days. Then it faded quickly. Most supernovae remain visible for months, gradually fading. A 2018 COW faded in weeks. It was like someone turned on a cosmic flashlight, shined it for a brief moment, and turned it off again. The light spectrum was also unusual. It did not match the spectra of known types of supernovae. The temperatures were extremely high, tens of thousands of degrees, and the explosion seemed to be expanding very fast, at a significant fraction of the speed of light. Astronomers quickly realized that 2018 COW was not alone. As they looked through archival data and continued monitoring the sky, they found more events like it. These ultra-fast, ultra-bright transients seem to be a whole new class of astronomical event. They are sometimes called fast blue optical transients, or FBOTs. The name describes them well. They are fast, peaking and fading in days or weeks. They are blue, emitting lots of ultraviolet light, indicating high temperatures, and they are optical transients, appearing and disappearing in visible light. As of today, we have found a handful of these events, not many, maybe a few dozen. They are rare or at least rarely detected, and we still do not fully understand what causes them. Several theories have been proposed. One idea is that they are the birth of black holes or neutron stars. When a massive star dies, its core collapses. If the core is heavy enough, it forms a black hole. If lighter, it forms a neutron star. This collapse releases enormous energy. Normally, most of this energy goes into blowing apart the outer layers of the star, creating a supernova. But in some cases, maybe the energy is released differently. Maybe it creates a jet that punches through the star's outer layers and shoots out into space. Such a jet would create a bright, fast transient that looks different from a normal supernova. Another idea is that FBOTs are the result of a star being torn apart by a black hole, a tidal disruption event. If a star wanders too close to a black hole, the black hole's gravity rips the star apart. The stellar material spirals into the black hole, heating up and emitting enormous energy. Tidal disruption events are known, and they can be very bright, but most are slower than FBOTs. They take months to peak and fade. FBOTs are much faster. Maybe they are a special type of tidal disruption where a small black hole disrupts a white dwarf or neutron star. A third idea involves collisions between two compact objects. Maybe a white dwarf collides with another white dwarf or a neutron star, releasing enormous energy in a brief burst. The truth is, we do not know. FBOTs are so new that we are still figuring out their basic properties. Every new detection gives us more data. What is exciting is that they represent something genuinely new. Astronomy has been studying supernovae for centuries. We thought we understood exploding stars pretty well. Then along came at 2018 COW, and it broke all the rules. It forced astronomers to realize there are types of cosmic explosions they had not anticipated. Now let me tell you about a star that should not exist. Its official name is HD 140283, but astronomers call it the Methuselah star, named after the biblical figure who supposedly lived to be 969 years old. The Methuselah star is about 190 light-years away from Earth. It is visible with binoculars if you know where to look, in the constellation Libra. It is an old star, a subgiant, meaning it has exhausted the hydrogen in its core and is starting to evolve off the main sequence. By studying such stars, we can learn about the universe's history. Astronomers can estimate a star's age using several methods. One method looks at the star's composition. The universe started with almost pure hydrogen and helium. Over time, stars have created heavier elements through nuclear fusion and supernova explosions. These heavy elements, which astronomers call metals, accumulate over time. So a star with very few metals probably formed early, before many generations of stars had enriched the interstellar medium. The Methuselah star has very low metallicity. It contains about 250 times less iron than the Sun. This suggests it formed early, when the universe was young and heavy elements were rare. Another method to estimate age looks at the star's nuclear fuel consumption. Stars fuse hydrogen into helium in their cores. Once they run out of hydrogen, they start fusing helium into heavier elements. The rate of these reactions depends on the star's mass and composition. By observing a star's properties, temperature, luminosity, composition, you can estimate how long it has been burning and therefore how old it is. When astronomers applied these methods to the Methuselah star, they got an uncomfortable result. The star's age came out to around 14 billion years, with error bars that uncomfortably overlap with the age of the universe itself. Here is the problem. The universe itself is only about 13.8 billion years old. We know this from multiple independent measurements: the cosmic microwave background, the expansion rate of the universe, the ages of the oldest star clusters. They all point to an age of about 13.8 billion years. So how can a star be around 14 billion years old in a 13.8 billion-year-old universe? The error bars technically allow for ages just barely younger than the universe, about 13.7 or 13.8 billion years, but it is cutting it incredibly close. That is uncomfortably tight. When this result first came out, some people suggested maybe our measurement of the universe's age was wrong. Maybe the universe is older than we thought. But as measurements improved, the universe's age became more certain, definitely around 13.8 billion years with very small error bars. So the problem must be with the star's age estimate. But how could we be wrong? The methods for estimating stellar ages are well established, based on solid physics. The key is the error bars. The Methuselah star's age is around 14 billion years, with uncertainties that technically allow for it to be as young as 13.7 or 13.8 billion years. That is just barely younger than the universe, technically possible. If the star formed very soon after the Big Bang, within the first few hundred million years, it could be that old. But even this is uncomfortable. The very first stars in the universe were different from stars today. They formed from pure hydrogen and helium with no heavy elements and were probably very massive and short-lived. The Methuselah star does not fit the profile of a first-generation star. Second-generation stars, which formed from gas enriched by the first supernovae, would have some heavy elements. The Methuselah star has a small amount of heavy elements, consistent with being a second-generation star. But second-generation stars would not have formed immediately after the Big Bang. It would take time for the first stars to live, die, and enrich the interstellar medium, maybe a few hundred million years. So the Methuselah star probably formed at least a few hundred million years after the Big Bang, making its maximum possible age about 13.5 billion years or less. The problem is that the observations keep suggesting it is older than that. Even with improved measurements and refined models, the star's age estimate stays around 14 billion years. The error bars have gotten smaller over time, which is the opposite of what we would hope. We would like them to encompass a younger, more comfortable age. So what is going on? One possibility is that our models of stellar evolution are wrong in some subtle way. Maybe low metallicity stars evolve differently than we think. Maybe there is a process we do not understand that affects their nuclear burning rates. Another possibility is that our distance measurement to the star is wrong. Age estimates depend on knowing the star's luminosity, and luminosity depends on distance. If the star is closer or farther than we think, its age estimate would change. Astronomers have measured the distance to the Methuselah star using parallax. As Earth orbits the Sun, nearby stars appear to shift position against the background of more distant stars. The Gaia satellite has measured parallaxes for billions of stars with unprecedented precision, including the Methuselah star. But there is still some uncertainty. Maybe the distance is slightly different, enough to bring the age estimate down to something more comfortable. A third possibility is that the star is simply younger than the best estimates suggest, and we are just on the unlucky end of the statistical distribution. When you measure something with uncertainty, sometimes the true value is at the edge of the error bars. Maybe the Methuselah star is really 13.5 billion years old, and the 14.5 billion year estimate is just a statistical fluctuation. As of today, the Methuselah star remains uncomfortably old. Astronomers keep refining the measurements, hoping to resolve the tension. But for now, it stands as one of the strangest things in the universe, a star that, according to our best measurements, seems to be older than the universe itself. Of course, it cannot actually be older. Something about our measurements or models must be off, but figuring out what is taking time. Now, here is something interesting to think about. All of these strange discoveries might seem unrelated. A radio signal from the 1970s, a star that dims irregularly, giant radio circles, structures that are too large, empty voids, cold spots in ancient light, radioactive elements in a star, an interstellar visitor, weird explosions, an impossibly old star. They seem like completely separate mysteries. But maybe they are not. Maybe they are all telling us the same thing. That the universe is more complex than our current models suggest. That there are processes, phenomena, or physics we do not fully understand yet. Think about it. The wow signal tells us there are radio sources we have not identified. Tabby's star tells us stars can behave in unexpected ways. Odd radio circles tell us galaxies can create structures we are only beginning to see. The giant arc and big ring tell us the universe might not be as uniform as we thought. The Boötes void tells us emptiness can be more extreme than our models predict. Each mystery on its own is just an oddity, but taken together, they paint a picture of a universe that is still surprising us, still showing us things we did not expect. This is actually normal in the history of science. When you are on the edge of understanding something new, you start seeing anomalies, things that do not quite fit. At first, they seem like isolated problems, but eventually someone connects the dots. Someone realizes these anomalies are all symptoms of something bigger, something we have not understood yet. That is how we discovered relativity. In the late 1800s, there were several problems in physics. The orbit of Mercury did not quite match predictions. The speed of light seemed constant regardless of how you measured it. These seemed like separate issues. Then Einstein came along and showed they were both explained by the same new theory. Relativity connected the dots. Maybe that is what is happening now with these cosmic mysteries. Maybe they are all pieces of a puzzle. Someday someone will figure out how they fit together, develop a new theory, or discover a new phenomenon that explains all of them at once. Or maybe not. Maybe each mystery has its own separate explanation. We will not know until we figure them out. But the possibility that they are connected, that they are all telling us something fundamental about the universe, is exciting. Some of the greatest advances in astronomy came from being wrong, from making observations that contradicted what we thought we knew. In the early 1900s, astronomers observed distant galaxies moving away from us, and the farther away they were, the faster they were receding. This did not make sense. Why would everything be moving away from us? But as they thought about it, they realized this pattern would happen if the universe itself was expanding. That observation led to the Big Bang theory. In the 1960s, astronomers discovered quasars, points of light that looked like stars but were incredibly bright, brighter than entire galaxies, and very far away. Nothing we knew about stars could explain how they could be so bright. Eventually, scientists realized quasars were not stars at all. They were the centers of galaxies containing supermassive black holes. This discovery changed how we thought about galaxies. In the 1990s, astronomers measuring the expansion of the universe expected to find it was slowing down. Gravity should be pulling everything back together. But they found the opposite. The expansion was accelerating. This made no sense. What could be pushing the universe apart? This observation led to the concept of dark energy, a mysterious force that makes up about 68% of the universe's total energy. We still do not really know what dark energy is, but we know it exists because the observations demand it. Each of these discoveries started with an observation that did not make sense. And each time, instead of ignoring the observation, astronomers followed where the evidence led. They changed their theories to match reality. That is what is happening now with the mysteries I have described. The reason we are finding so many strange things in space right now is not because the universe suddenly got stranger. It is because our tools got better. We can see things we could not see before. We can measure things we could not measure before. The wow signal was detected by a relatively simple radio telescope in 1977. Today we have much better instruments, the Very Large Array, ALMA, the upcoming Square Kilometre Array. If the wow signal happened today, we would learn so much more about it. Tabby's star was discovered by the Kepler Space Telescope, which launched in 2009. Before Kepler, we could not monitor thousands of stars continuously. Kepler gave us that capability. Odd radio circles were discovered because we built a SCAP, a new type of radio telescope that can survey large areas of the sky quickly. The CMB cold spot was mapped by satellites like WMAP and Planck. Each advance in technology opens new windows. Each new instrument reveals things that were hidden before, and we can be confident that future instruments will reveal things we have not imagined yet. In the coming years, we will have even better tools. The extremely large telescope is being built in Chile. When complete, it will have a mirror 39 meters across, able to see incredibly faint and distant objects. The square-kilometer array will be 50 times more sensitive than any current radio telescope. If there are radio signals out there like the WOW signal, it will find them. NASA is planning new space telescopes to look for signs of life on exoplanets and study the early universe. And every time we build a better telescope, we find surprises. Every single time. There has never been a case where we built a more sensitive instrument and found exactly what we expected and nothing more. The universe always surprises us. So we can be pretty confident that in the coming decades, we will discover more strange things. More mysteries to puzzle over, more observations that do not quite fit our theories. And that is exciting because mysteries drive progress. They force us to think harder, to question our assumptions, to develop new ideas. You might wonder why some of these mysteries have been around for years or even decades without being solved. The WOW signal was from 1977, almost 50 years ago. Why have we not figured it out yet? There are several reasons. First, in many cases, we simply do not have enough data. The WOW signal lasted 72 seconds. We have one data point. It never repeated. That makes it incredibly difficult to study. Imagine trying to understand an animal based on seeing it once for 72 seconds. One brief observation is limiting. Second, some phenomena are complex. Tabby star has lots of data, but the dimming pattern is irregular, and multiple things might be happening. Third, measurement precision can be an issue. The Methuselah star's age depends on combining multiple uncertain measurements, and small errors can add up. Fourth, some mysteries require technology we do not have yet. Space telescopes are expensive and take years to build. Fifth, some require a theoretical breakthrough, a new way of looking at the problem. The discovery of dark energy took years, from the first confusing observations to acceptance that something new was needed. But here is the important thing. The mysteries I have described are all being worked on. Scientists are observing, measuring, thinking, debating. Progress is happening even if it is slow. And eventually, these mysteries will be solved. Maybe not all of them in our lifetime, but someday, these strange discoveries will teach us something important about how the universe works. When you look up at the night sky, remember that you are looking at a universe full of wonders. Some we understand, many we do not. The WOW signal happened. Tabby's star is dimming. Odd radio circles exist. The giant arc and big ring are out there. The Boötes void is almost empty. The CMB cold spot is too cold. Przybylski's star has radioactive elements it should not have. Oumuamua passed through our solar system and accelerated strangely. A 2018 cow exploded in ways we cannot fully explain. The Methuselah star seems older than the universe. These are not hypotheticals. They are real observations. And they are all invitations to wonder, to question, to explore. The universe is strange. It is full of mysteries. And every mystery is an opportunity to learn something new. That is what makes astronomy so exciting. That is why scientists stay up late analyzing data, building models, trying to explain the unexplainable. Because the universe is strange, and strange is wonderful. Let me leave you with one last thought. Every mystery I have talked about represents something real, something that is out there right now doing whatever strange thing it does. The universe does not care about our theories or expectations. It just does what it does. And when we observe it carefully, we find things that surprise us. That is both humbling and exciting. Humbling because it reminds us how much we do not know. Exciting because it means there is always more to discover. Science is not about having all the answers. It is about being honest about what we do not know. The scientists studying these strange phenomena are not embarrassed that they do not have explanations. They are excited because mysteries are opportunities. Every unsolved problem is a chance to learn something fundamental about how the universe works. So the next time you hear about a strange discovery in space, do not think of it as a problem. Think of it as an invitation to explore, to discover, to learn. Because the universe is full of strange things. Some we have found, many more we have not. And each one, when we discover it, teaches us something. That is the adventure of astronomy. That is why people dedicate their lives to studying the cosmos. Because out there in the darkness between the stars, mysteries are waiting. Strange signals, dimming stars, giant circles, impossible structures, ancient voids, cold spots, radioactive elements that should not exist, interstellar visitors, unexplained explosions, stars older than they should be. These are the things that keep astronomers awake at night. Not because they are scared, but because they are fascinated. And if you have made it this far, if you have listened to all these strange stories, then maybe you are fascinated too. That is good. The universe deserves our fascination. It deserves our curiosity. It deserves our best efforts to understand it, because it is strange, wonderfully, beautifully strange. Thank you for joining me on this journey through the strangest things we have discovered in space. If you enjoyed this exploration, please hit that like button and subscribe to the channel. And remember, the universe is full of mysteries. We have barely begun to understand it. There are strange things out there waiting to be discovered. Things that will puzzle and amaze us. Things that will challenge everything we think we know. That is not a problem. That is a promise. Sleep well under the stars. And remember, somewhere out there, strange things are happening. Things we do not understand yet. Things that one day might change everything we know about the cosmos. Good night.